Welcome to part 2. To recap, we're looking at how we can combine trig functions together. If we have some multiple of sine theta and some multiple of cos theta added or subtracted, and we want to either solve equations involving those, or easily identify the extreme values, the maximums and minimums, or we want to deal with a modeling question that involves various trig functions added together to make things look complicated, we can convert our two separate trig functions that are trying to be added or subtracted into one single trig function. The complexity, the detail of those two separate ones is taken into account by translating a sine or cos graph to the right or left and then stretching vertically. That's what the alpha and the r give you. We're going to work through an example to see how it's done. So we start by stating this as an identity. We are claiming that 3 sine x plus 4 cos x can be written as r times sine of x plus alpha for some values of r and alpha. If we assume that this is possible, then we use that assumption to go through and find the values of r and alpha that will make it true. Now, the right hand side is the one that we can most easily break apart and work with. So we use the addition formulae to turn that into sine x cos alpha plus cos x sine alpha. And of course, the whole thing is multiplied by r. The next bit, this is really clever and important. We need to remember that what we're dealing with here is not just an equation we're trying to solve. This is an identity we're trying to make true. If this is going to be identical, it means for any value of x, the left-hand side must match the right-hand side. What that means in practice for us here is that however many sine x's you've got on the left, it must be the same as the number of sine x's you have on the right. This is sometimes referred to as comparing coefficients. We're going to look at how many sine x's you have, the coefficient of sine x on the left, and we compare it to the coefficient of sine x on the right. And we do the same thing with cos x. So we can now say that 3 lots of sine x must be identical to r times cos alpha times sine x. That's the first term from the bracket up at the top, multiplied by the r term out at the front. But similarly, 4 cos x needs to match r times sine alpha times cos x. The bits we care about in there are the coefficients, like I said. So the equation on the left, that equation gives us the coefficient of sine x on the left hand side and the coefficient of sine x on the right hand side of the big equation above. Similarly for the other one. So all we need to do now is solve these two. Now we've got two equations and we have two unknown values. So in theory, it should be possible to solve these simultaneously. There's a few different ways to do it, and you might already be thinking in terms of dividing one by the other to eliminate r. But I'm going to use a bit of a trick for this first one, and then we're going to talk about how that trick will make this process a lot quicker in general. We don't normally do exactly what I've done here. Normally there's a bit of a shortcut we can do at the beginning, which we're going to find very helpful. We're going to find a way to identify r before we begin all of this trig nonsense. So look what happens here. I'm going to square both sides of both of these equations. 3 squared equals r squared cos squared alpha, and 4 squared equals r squared sine squared alpha. Why? Well, cos squared add sine squared is 1 regardless of the angle that's involved. So cos squared of alpha plus sine squared of alpha is going to be 1 because they both refer to the same angle. That means I can add the two left-hand sides of these two equations and add the two right-hand sides and set them equal. I can pull out r squared as a common factor, and straight away you can see that because cos squared add sine squared is 1, r squared must be 25. And therefore r is 5, right? Or potentially negative 5. Now it turns out you could use negative 5. It's not a problem. That's an equally valid solution. What you'd be doing there essentially is multiplying by a negative vertical scale factor. You'd be flipping over your sine or cos graph. And that would mean you'd need to translate by a different amount. So your alpha value would be pi radians bigger or smaller than it otherwise would have been. Generally speaking, by convention, we go with a positive value for r. Essentially, we get to choose a value here and use that value. So it's traditional to use the positive value to keep life simple. So we're going to choose a value that matches. And now if you look closely, you'll notice that the 9 and the 16 that we used to find r? Well, they came directly from the 9 and the 16 in these equations above, which came from the 3 and the 4 over here. In fact, you can trace those 3 and 4 all the way back to the very beginning. Right up here, at the very beginning, usually what we do is we say r equals the square root of 3 squared add 4 squared. Because of Pythagoras, which is essentially what sine squared add cos squared equals 1 is telling us, we can use that result straight away and we calculate the value of r before we do anything else. That means, for instance, here we can put 5 times that big messy bracket. And in this next line, instead of r, we can put 5. And that gives us an interesting result. It means we end up here still with 2 equations, but now 2 equations and only one of the unknowns is unknown. The other one we now know. So 2 equations, 1 unknown. It feels like we've got a bit of redundancy here. We don't need them both. And if you try solving, you'll probably feel the same. You'll end up with the same answer from both. But you've got to remember that we're dealing with sine and cos, and there isn't just one answer for cos alpha equals 3/5. There isn't just one answer for sine alpha equals 4/5. There are multiple answers for both of them. What we're looking for is a value of alpha that matches both requirements. It must simultaneously satisfy cos alpha equals 3/5 and also at the same time satisfy sine alpha equals 4/5. Now it feels like I'm banging on about this too much because of course this is the same value we've got from both, so of course it fits both and we're good and we're done. But in some cases you'll find that, particularly if you're doing this for yourself, you're trying to solve an equation and the question is not giving you a choice, it's just you need to solve an equation involving sines and coses added or subtracted, you might choose r sine x minus alpha, or r cos x plus alpha, or r cos x minus alpha. And if you choose a different one to the optimal choice, it's still perfectly possible. It just means that you might end up needing to translate by, say, a negative number, or translate by an obtuse angle. And if that happens, then your principal value will not necessarily match. You don't need to panic in that case, you just need to look a bit further afield. You need to look for additional solutions by considering the graph for each of those. So if you've got a cos value of 0.7 and your sine value isn't 0.7, well maybe your sine value is minus 0.7. And if cos of something is 0.7, you could try your 0.7 in the sine one, you could try your minus 0.7 in the cos one, you could see what happens. You can play around with the next solution that comes out from each one. You can go a bit further afield if you need to. In most cases, that's not going to be a problem. The solutions you get will match, but I want to stress the point that they don't necessarily always have to, especially if you're creating this from scratch for yourself. So I'd always recommend you check that the solutions you get from each one matches. So here's the final result. You rewrite that line we had right at the very top, but you replace r with a value for r, and you replace alpha with the value we now have for alpha. And you should find that this single trig function that's been shifted to the left by 0.927 radians and stretched vertically by scale factor 5 perfectly matches 3 sine x plus 4 cos x. Here's the general pattern that you need to be following. Find r right at the very beginning using a squared plus b squared equals r squared. And that will work for any a and b, positive or negative, it makes no difference. Then you apply the addition formula. You will either have sine of x plus alpha, or sine of x minus alpha, or cos of x plus alpha, or cos of x minus alpha. Use the appropriate formula and break apart your term into 2 pieces. Equate the coefficients of sine and cos. Sine x and cos x we had. Sine theta and cos theta is also common. Remember the bits with the variable in it. They're the things that you care about the coefficients of. So that's why I've taken out the 3 and the 5 cos alpha up at the top here. Those two are the bits that need to be the same because those are the bits that are multiplied by the sine x term. Once you've identified those, you need to make sure you've got an alpha that fits both of the equations you produce, and finally you rewrite your original expression. Now it's all ready to do all the useful things with. So here's the first of the things that we can do with this, solving equations. If we come back to this example, Notice that we've got a range 0 to 2 pi. There is only one really important thing that happens here, and that is making use of our identity. 3 sine x plus 4 cos x can be rewritten as 5 sine x plus 0.927. So we change the equation into that, and suddenly you'll notice we've got a trig equation with one single trig term in it. This allows us to solve it. It's important to note as well, we've got a slightly different range. The original range, the values for x that I care about, are between 0 and 2 pi. But because I've got a translated curve, I need to be thinking about the values of x plus 0.927. Which means I need to look at values that are a bit bigger than 0 and values that go up to a bit higher than 2 pi. So that's the range I'll be looking for when I initially do the inverse sine of 2/5. Well, that's the first thing I do. I'll divide by 5, I'll do inverse sine of 2/5, and the first solution from the calculator does not fit my range, but I need it to find the other ones. So inverse sine of 2/5 is 0.412 radians. Then if I find the next solution using the symmetry of the graph, for sine, I can do pi minus the original value, so I get 2.730. And then I can also add 2 pi to any of my solutions to generate the next one along using the period of the sine wave 2 pi. So 0.412 plus 2 pi gives me the 6.695. If I do 2.73 plus 2 pi, it gets me an answer bigger than 7.21. So that one's outside the range. These two are the only two valid solutions that I've found. But remember, these two are solutions to x plus 0.927. So these are the values of x plus 0.927. To get the values of x, I need to subtract 0.927 from each of them. You can then do a final check, see if these two numbers match the original range. Are they between 0 and 2 pi? And if they are, then that's a good sign. Even better, if you can substitute them back into the original equation, if 3 lots of sine 1.8 plus 4 lots of cos 1.8 is around 2, then you're off to a good start. The last thing to check, for this I can easily draw a graph with graphing software. It's not quite so straightforward if you're working on an exam question, but with a graph I can convince myself that those solutions look sensible. Even without a graph, it's worth noticing that this process does not change the period of the graph. So if you're looking between 0 and 2 pi and you'd usually be expecting 2 solutions, you should still be expecting 2 solutions. The graph may have been translated a bit sideways and it may have been stretched vertically, but it's still fundamentally a sine or a cos type graph with the same frequency as an ordinary sine or cos graph. It wobbles up and down with a period of 2 pi. The second useful thing we can do if we're able to convert two different trig functions added into one single trig function is really quickly and easily identify the maximum and the minimum values for that and where they occur. So with our function y equals 3 sine x add 4 cos x, replace 3 sine x add 4 cos x with our new improved single trig function, which has just been shifted sideways and stretched vertically. The range is going to be different again. What we care about here though is just the maximum and the minimum points. Potentially we ask for them within a certain range, or they might just ask a question that involves finding the gap between two maximum points for a particular graph, or it might be to work out the size of the gap between one point and another point. In this case, all we need to notice is that sine of something is always between 1 and -1. So 5 lots of sine of something is always between 5 and -5. All we need to do then is identify when that occurs. Well, sine takes its maximum value when the input is pi by 2. So the maximum will be 5, and it happens when it's doing sine of pi by 2, when x plus 0.927 is pi by 2. You could, if you weren't quite so confident with this step, just solve, put 5 in. 5 equals 5 sine x plus 0.927. Solve that as an ordinary trig equation and your solutions will come out. You'll find yourself solving sine of something equals 1, and that's where the pi by 2 comes from. Also, we can get the minimum value. If we have y equals 5 lots of sine something, it will go as low as -5. And that happens for a sine graph when the angle is pi. Again, we can have a quick look at a graph here to convince ourselves that we're on the right lines. There is a value at 0.644, it looks like, and another value at 2.2 something. Those are going to give you a maximum and minimum points. The final thing I want to go through is an example of a modeling question, partly because they look so meaty and scary, but they're really quite straightforward once you get into them. This tool is such a powerful tool that it allows us to solve these things that would otherwise be really complicated and or impossible. So we'll start with this. Express 65 cos theta minus 20 sine theta in the form r cos theta plus alpha. You'll notice, as I said, the exam question will very often give you the format they're looking for in order to guide you in the right direction. We've got a positive number of cos thetas, a negative number of sine thetas, so it's going to make the most sense to use cos theta plus alpha. But they're not expecting you usually to make that nuanced decision. They're expecting you just to follow the recommendation they've suggested. And they also state the standard condition that r is greater than 0. They don't always say that, but you can always assume it anyway. And because they've chosen a cos with a positive, they already know that you'll be able to do it by shifting to the left by an acute angle. Theta plus alpha, where alpha is an acute angle. So how do we do this? Well, it's the same method we've seen before. It looks a little different with cos, which is why I've chosen this one to go through as the example, but r is calculated in exactly the same way. This does simplify a bit, but I'm going to leave it in this form. The cos formula, r cos theta plus alpha, cos A plus B gives cos A cos B minus sine A sine B. So don't forget the negative in there. With sine, the signs match. With cos, the signs are contrary to each other. Now, when we break it apart and look at each piece separately, we have to remember to look at what cos theta is multiplied by on the left and set that equal to whatever cos theta is multiplied by on the right. And on the right there are two things. It's the root 4625 and the cos alpha, and that's why both of those terms appear in this equation. Well, that one's all well and good. This one should also be fine. You either include the negative on both sides or you don't include it on either side, but you need to be all or nothing, because otherwise you'll get signs mixed up and your numbers won't match. We have minus 20 sine theta, and we have minus root 4625 sine alpha sine theta. So those are the things that need to match up. When you simplify and solve, you should find that both of your primary solutions match. That will almost always be the case if they give you this solution. And in fact, if you know you're dealing with an acute angle like this one, then you can expect that the primary solutions are going to match. Like I say, they'll generally give you this format, the r cos theta plus alpha or r sine theta minus alpha, whatever's going to be the most appropriate for your question. So we've got the alpha value and we've got the r value, and it was 4 lines of writing. So it's not too tedious, and that's 4 marks worth you've managed to successfully rearrange. The bulk of the marks in this question are for making use of that rearrangement. So here, I've written out clearly exactly what we've done, because we are going to be relying on that throughout the rest of the question. Most of the rest, if not impossible to answer without this, is certainly very tricky. People never successfully answer this question unless they are making use of a result from part A. Now, I want to point out something about H at this point. The city is building a large circular wheel as a tourist attraction. This is where the modelling comes in. The height of a tourist on the circular wheel is modelled by a particular equation. H is the height of the tourist above the ground in meters, and T is the number of minutes after boarding, all angles given in radians. Firstly, you should recognise some similarities between the expression you are given here and the expression you were working with in part A. That is not coincidental. They're there for a reason. If you have a part B, particularly if it looks complicated, always ask yourself how it connects to part A. I've noticed, for instance, that if we take out a factor of -1, the stuff remaining in the bracket almost perfectly matches the stuff I had in part A. In fact, provided I recognize that we're dealing here with 0.2t and previously we were dealing with theta, that's all I need to notice in order to allow me to convert these. Wherever theta appears in my original statement that I've written down at the bottom here, I can replace theta with 0.2t. And that's exactly what I do here. If I recognize that 0.2t is theta, then the entire section that I've put in brackets for h, 70 minus something, that entire thing can be replaced with 70 minus my new expression. Why we do that will become much clearer once we start solving problems involving the height and time. Part B, for instance, the maximum height of the wheel. Well, remember that cos varies between 1 and minus 1. So if you multiply it by something, that something becomes the value which cos varies between, that number and the negative of that number. If you then subtract or add that to something else, you need to combine those as well. So what I've noted here is that we could put -1 for cos. That would be the extreme most negative number that cos would ever produce, and that gives the largest positive value we can get for h. If on the other hand you made cos equal to +1, you would get a value much smaller than 70. In fact, I think it comes out to around 2-ish. So 70 plus about 30, what would it be? 70 plus about 68, or 70 minus about 68 is what's happening. Root 4625 is something in the region of 68. It's a bit less than 70 because root 4900 would be 70. So that's the maximum height of the wheel. That's the greatest that h ever gets to, and all we needed for it was the value of r, because that's the key that tells you how large that term gets. The time for one complete revolution. This is asking for the period of the graph, and it's often something that people struggle with here. We don't need to worry about how far vertically the graph has been shifted, that's 70 meters. We don't care how much it's been stretched vertically, the root 4625. We don't even care how much it's been translated horizontally. The only thing we care about is whether the period, the frequency of the graph has been changed. Does it wobble up and down more frantically now because it's had a stretch in the x direction, or does it go up and down more lazily because it's been stretched by a number bigger than 1? If you stretch by a scale factor of 1/2, for instance, then you will get a higher frequency. It wobbles up and down twice as often. If you stretch by a scale factor of 10, then it's going to be a lazier up and down. It'll take 10 times as long to complete a cycle. The time taken for a complete revolution we can get directly from the period, but notice that 0.2t refers to a horizontal stretch of scale factor 5. We've multiplied by 0.2, so this is equivalent to f of a fifth x, stretching by scale factor 5 in the x direction. Everything is now more spread out, and that means instead of a cycle being completed in the space of 2 pi, the cycle is going to take 10 pi. And 10 pi is about 31.4 minutes. Part D, this is the most sophisticated bit of it, I think. It takes a bit of thought. The number of minutes the tourist will be over 100 meters above the ground in each revolution. So over the course of a single cycle, perhaps you would define it as from 0 to 10 pi, since you now know that the revolution time is 10 pi. You would look at the times when the height is greater than 100 meters. The best way to do this is to write exactly what you know. We look for the values of t for which h is greater than 100. We substitute that in. This is h. Messy though it looks, it's nicer than the original version because there's only a single trig function. And in this case, we've had horizontal translations, horizontal stretches, vertical translations, vertical stretches. There's all sorts going on, but it's still, at heart, deep down, it's a trig function. It's not going to forget its roots. It's going to wobble up and down like any other trig function. The only difference is how quickly it wobbles up and down, how much it wobbles up and down in terms of how far up and how far down it goes, and where it is, where it's positioned, whether it starts in a funny place, whether it's higher or lower than it would normally be. To solve an inequality like this, we're going to need to either change sides, because we've got a negative number in front of cos, or we'll need to divide by a negative. Either way, we'll end up reversing the inequality sign in some sense. We'll have cos of something is less than this negative number. And at this point, I would stop and draw a cos graph. Not the big messy cos graph that this represents, although I will show you that in a moment, but just a standard run-of-the-mill basic cos graph. The cos graph that this cos graph used to be before it got hit with all of these upgrades and amendments that it's had applied to it. A cos graph, and we're asking cos of something is less than negative, well, negative about a half, that number is, I think. So all we need to do is consider on our cos graph, when is it below minus a half-ish? And we can see that that happens between 2 points. If we can find the values at these points, then we can say between these points is where we want to be looking. That's where the cos graph satisfies this inequality. So that's what we do. The critical values are the values we get when we say cos of 0.2t plus 0.2985 equals negative 30 over root 4625. That will give me these two values. And when we rearrange and simplify, we'll get 8.64 and 19.97 for t. And then think back, look back at the question. T is defined as the number of minutes after boarding. And the question is asking, what is the number of minutes the tourist will be over 100 meters above the ground? H greater than 100 corresponds, like we said, to this cos graph being less than 30 over root 4625 negative. And that happens between these two t values. So subtract one from the other, and we get the total time for which we are above 100 meters. The last thing I want to do is look at the actual graph. It's always worth doing, even if it's not strictly required by the question. Whenever you're working on one of these and it's not in an exam situation, then it's a good idea to pull up GeoGebra or Wolfram Alpha and draw the sketch. Hopefully you can see here that our idea of having an amplitude of about 38 makes sense. It's been stretched by a scale factor of 38. It goes, oh, sorry, 68, something like that. Root 4625, nearly 70 is what we got. The height of the middle is somewhere around 70, and it goes up as high as nearly 140 and down almost as low as 0. So we can see the effect of the vertical stretch already. Horizontally, you can see the effect of that. I've scaled the graph so it fits comfortably on the screen, but if you look at the numbers on the bottom, you'll find that we have to go a long way before we complete a full cycle. We go from the bottom, or close to the bottom at the very beginning, up and down and back to where we started, and it takes more than 30 minutes. That's the effect of stretching by a scale factor 5 in the x, or in this case the t direction. The height, the vertical axis, you can see oscillates between very low but not quite 0 and very high, just under 140. And that makes sense for a Ferris wheel, something like that. It's going to come down, it's going to go up, and the speed with which it moves up or down depends on where you are on the Ferris wheel. If you're near the top, then for quite a few minutes you remain near the top. You're moving mostly sideways when you're near the top. You're not moving up and down as quickly as you are when you're halfway up or halfway down. And similarly, at the bottom, you're mostly moving sideways. Even if the entire wheel is traveling at a constant rotational velocity, most of your motion when you're at the bottom is in the sideways direction, and only a little bit of it is in the vertical direction. You should now be able to tackle a bunch of questions from that exercise, 7G, and hopefully make sense of some of the later bits in the book. I'd recommend you try some of the mixed exercise questions, and especially get your teeth into some of these modeling questions. The technique you're learning with Rcos theta minus alpha, R sine theta plus alpha, etc. is most usefully understood in the context of these modeling questions, where they will ask you for maximums, minimums, they'll ask you questions about the period of the graph, and recognizing the value of turning something which involves two different trig functions somehow combined by adding and subtracting into one single trig function. That is the key thing that allows you to A, solve equations, and B, identify maxima and minima, C, tackle big nasty modeling questions like this and get a handle on exactly what's going on.